Hello, and welcome back again to Chapter 4 of Physics 41, University Physics 3. So in the previous lesson, I forgot to show the simulation of a capacitor with a dielectric. So I'm just going to show here this one again. So we have here an uncharged capacitor. So we will now charge it to 1.5 volts. So this is actually exactly our problem in the previous lesson. So you have a parallel plate capacitor. The area is 100 millimeters squared. The separation distance is 5 millimeters. And you will have a dielectric material with dielectric constant of 5. So you will notice in this case, the original capacitance is this is actually 1.77 times 10 to the negative 13. It's just now to the power of negative 12. So it's 0.177 or 0.18. And this is the the charges on the plate. 2.66 times 10 to negative 13 coulomb. The energy is almost 2 times 10 to negative 13 joules. So since the capacitor is now charged, we will now disconnect it from the battery. And we now have a charged capacitor. So you will notice that when I place the capacitor, sorry, when I place the dielectric in between the charge or in between the plates of my capacitor, what happens? From point 18, the capacitance actually changes to 0.89. That's actually times 5 of your times 5, since the dielectric constant is 5. You will notice that the plate or the charges on the plates remain the same. It doesn't change, but the energy from 2 or 1.99, it will be divided by 5, so it will become 0.4 times 10 to the 13 joules. So this is what happens when a dielectric is inserted in between the plates of your capacitor. So far we have discussed about capacitance, charge, and voltage. So they all revolve around these equations. So for this lesson, we will now go into basic capacitor connections, the series and the parallel connections. So the first connection is the series connection. So when your two capacitors are connected in series, it means that one plate of the capacitor is connected to another plate of a capacitor, but their other plates are not connected with each other. So to put this into some analogy, forgive me of my drawing. These are two people connected in series. So only the one hand of the first person is connected to the other hand of the second person, but their other hands are not connected to each other. That's a series connection. So that is true for all circuit elements, not just for capacitors. So that's a series. That's how you connect two objects in series, or in this case, two circuit elements in series. So when you connect them in series, you can actually replace this connection by just one equivalent capacitor. And the capacitance of that equivalent capacitor, called equivalent capacitance, is just given by this. So it's the inverse of the sum of the inverses of the capacitors connected in series. Take note this, there's a plus dot 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 here. So depending on how many capacitors you connect in series. So if you have 3 capacitors connected in series, it will something like look like this. Or if you have 4, it will somewhat look like that. Oh, so you have 4 capacitors connected in series. Okay. Now, if you will notice, the equivalent capacitance of capacitors in series is always less than the individual capacitances. For example, if you have two 1 farad, this is 1 farad and that is 1 farad. So the equivalent capacitance, if they are connected in series, will be, you have 1 over 1 farad plus 1 over 1 farad. So 1 plus 1, you get 2. And then inverse, that's the power to the power of negative 1. So inverse of 2 is 1 half. So if you connect two 1 farad capacitors in series, you will actually get 0.5 farad or 1 half farad. Now, you may be wondering, why would I need a why would I need to connect them in such a way that the capacitance will decrease? Because there are instances that you you need a 0.5 farad in your circuit, but what you have are only two 1 farads. So in order to have a 0.5 farad capacitor, then you just connect the two 1 farad capacitors in series. So it depends on your need. If you want a smaller capacitance, but you only have large capacitors, then just connect them in series to lessen their capacitance or equivalent capacitance. Now, capacitors connected in series, or a series connection rather, is what we call a voltage divider. So this is true not only for capacitors but to all electrical circuit elements. Elements connected in series have the voltage divided. So if the total voltage of this network is V, then this V, this potential difference, will be divided among the circuit elements connected in series. In this case, the capacitors connected in series. So the V will be divided into V1 here and then V2 here. So if you add V1 and V2, you will get V. But of course, if you have more than 2 or 3, just add their corresponding voltages. Now, one thing that's one property of the series connection is that the charge remains the same. So the total charge, the charge of this network is Q. So the charge of this Q1 is also Q. The charge of Q2 or capacitor 2 is also Q. So the charge remains the same, but the voltage is divided. Okay, let's now go to the second basic circuit connection. So what if your capacitors are connected in parallel? Okay, so what is the difference between a series and a parallel connection? So in a series connection, only one plates or only one plate of a capacitor is connected to the other plate of a capacitor. But in series, you connect both of their upper plates and you connect both of their lower plates. So to put this in an analogy, so we go back again to my stick drawings. This is person 1 and this is person 2. If they are connected in parallel, then both of them are holding each other's hands. That's basically a parallel connection. So that one. So it's a parallel connection. If only one of the hands are connected or one of their plates are connected, then that's a series na connection. Okay. So when, again, similar with the series connection, you can actually replace these two parallels connected in series as just one equivalent capacitor. And the equivalent capacitance of that capacitor is just the sum of the individual capacitances of the capacitors connected in parallel. So you just add them directly. So the equivalent capacitance of capacitors connected in parallel will result in a larger capacitance. So for instance, you only have two 1 farad capacitors available lying around and you need a 2 farad capacitor, so just connect the two in parallel. So unlike the series connection, in a parallel connection, the voltages are all the same. But the charges are now divided. So if the total charge of this network is Q, then part of that Q will go to Q1 and part of that Q will go to Q2. So it's a charge divider. So this is true for all circuit elements, not only for capacitors. So a parallel connection is a charge divider in terms of capacitors, but when you go to resistors, it's a current divider. Okay, let's go directly to an example. Okay, capacitors in series and parallel. So you have two capacitors with capacitances C1, 3 microfarad, C2, 6 microfarad. So if these two capacitors are connected, find the equivalent capacitance if they are connected in A, series, and B, parallel. Okay, let's start with letter A, series connection. So if they're connected in series, then we use the series formula, 1 over C1 plus 1 over C2, then inverse. So you will get 1 over 3 microfarad plus 1 over 6 microfarad, and then you get the inverse. So you will notice I didn't write the units here, but instead I will write the final unit here. Take note that the microfarad unit will go to the numerator because there's an inverse here. So 1/3 plus 1/6. So this is essentially 2/6 plus 1/6. You get 3/6 or 1/2. Inverse of 1/2 is 2. So you get 2 microfarad. So you will get 2 microfarad. Now, for letter B, how about you connect them in parallel? So it's just very easy. I will no longer solve this because the parallel connection is just an addition formula. So just add it through. 3 microfarad plus 6 microfarad, of course, you will get 9 microfarad. So it's easier to solve for the equivalent capacitance if your capacitors are connected in series, in parallel. So just add them up. Okay, let's have another example. So let's now have a capacitor network. So find the equivalent capacitance of the combination shown. So this is the combination. So you have 1, 2, 3, 4, 5 capacitances or capacitors. So to make this more clear, I'm gonna label these capacitors. So this will be my C1, this will be my C2, this will be my C3, this will be my C4, and this will be my C5. Now, if you are given a capacitor network, always look for the basic connections, the basic series and parallel connections. So here you will notice that C1 and C2 are connected in series. C3 and C4 are connected in parallel. And those are just the basic connection. C3 and C5 are not connected in series because there's a junction here at this point. So that is not, there's C3 and C5 are not in series. Similarly with say C2 and C5, that's also not a series connection. So that's neither series nor parallel. So what we will do is just simplify the network until it becomes just one equivalent capacitor. So we can actually combine these two, C1 and C2, to get an equivalent capacitor, say C1, 2. So we use the series formula. So C1, 2, for instance, is just equal to 1 over C1 plus 1 over C2 to the power of -1. Oh, really klaro. So you will get 1 over 12 plus 1 over 6 to the -1 microfarad, and that will give you 112 plus 1/6 is actually 2 over 12. So you have 3 over 12, or 1/4, and 1/4 to the power of -1, or inverse of 1/4, is 4 microfarad. So that's what you get here. So the series connection of a 12 microfarad and a 6 microfarad capacitor is equivalent to a 4 microfarad capacitor. Okay, so that's it. So now we now have simplified this. So from here we see that C4, C3, and C12 are connected in parallel, because all of their upper plates are connected together and all of their lower plates are connected together. So the three of them are connected in parallel. So we can actually replace C4, C3, and C12 by an equivalent capacitor, say C1, C1, 2, 3, 4. So basically just add, because it's parallel connection. So 3 plus 11, 14 plus 4, you get 18 microfarad. So I will no longer show that solution to you. That's just basic addition. Okay, finally, our circuit is reduced to 2 capacitors in series. So we can then combine these two, use the series formula to find the equivalent capacitance. So in this case, if you get, so the equivalent capacitance, it's no longer necessary to use C1, 2, 3, 4, 5, because this is now the final capacitor. So we will now use the equivalence, C equivalence. So this is basically 1 over C1, 2, 3, 4 plus 1 over C5, the -1. So you get 1 over 18 plus 1 over 9. So 1 over 18 plus 1 over 9. 1 over 9 is 2 over 18. So you will get 3 over 18. So 3 over 18 is 1/6. 1/6 to the power of -1, or inverse of 1/6, is 6 microfarad. So in this part of the lesson, you actually don't, pwede actually mata-mata. So you can just do this by eye, no longer. But don't do that in your solution. You must show your solution. Don't copy me. Nagmata-mata lang. Okay. So the final result will be 6 microfarad. So this network of capacitors, 5 capacitors, is just equivalent to a single capacitor with a capacitance of 6 microfarads. And that's it. That is essentially the end of this chapter. But we will have one more lesson, one video lesson to go, and it's just basically just more examples in this chapter, so that we can deepen our understanding on capacitors with dielectrics. So I will see you again for the final lesson, which is just more examples on this chapter.